Hello, in this video, we'll be looking at a very short, quick review of chapter P. So these are the chapters of the sections under chapter P. We have section P2 about real numbers. P3 is about integer exponents and scientific notation. P4 it's on rational exponents and radicals. P5 is about algebraic expression, and P6 is about factoring. P7 is about rational expression, while P8 is about solving basic equations. So we'll start with P2. And what is P2? P2, it's about real numbers. And so in this P2, we're going to be starting with the classification of numbers. How do we classify numbers? Real numbers. So real numbers, there are different types of numbers which are invented based on their needs. Some are for counting, some are used for fractions and all of that. So let's start with the first one. Let me start here, which I will call the natural numbers. And these natural numbers, we use capital N to denote natural numbers. And another name for these natural numbers is called counting numbers. So you can put it inside here. Let's say just counting numbers. And here, basically, this starts from the set of what? The number 1, 2, 3, 4 continuously. So they are used for counting. Then the next one that we can get in addition here is what we call the whole numbers. Now I'll tell you a reason why I'm starting from below. We're going somewhere. So the whole number is just a set of what? Of natural number, but what? With the addition of 0 continuously. So you can see the difference between a natural number and a counting and a whole number is just 0. Then we have the next one, which is called the integers. So integers are denoted by capital letter Z. Now, so when we say integers, so integers is just what? It's just the collection of both the positive natural number, the negative natural numbers, and also what we say zeros. So it means we can start from here, and let's say we start from -3, -2, -1. So you see all of these they are natural numbers, but now with negative, right? Then we have 0, which is like the center in a way. Then we have 1, 2, 3 continuously. So this is what we call the integers. So if you look the integers, if you start from here, this is nothing but what? The natural. So we call this one the positive integers. And this side, we call them the negative integers. And then we have a 0, which is like dividing the dividing the integers into two parts, the negative and the positive part. Then here we will go to now what we call the rational numbers. So what is rational number? So rational number is actually any number that you can write in this form. So rational number is used by letter Q, denoted by letter Q. So it's any number you can write in the form of A divided by B, I mean in the form of fraction, where A, B are what? Are integers, and B must not be what? Must not be 0. So this is simply any number you can write in fraction form. Yeah, it's called an integer. But there are two types of these rational numbers. So let me put the category here before we put an example. They are divided into two. Let me do it this way. There is what we call them the terminating decimals. And we call it the non-terminating decimals. Okay. Repeating decimals. Okay, so this I'll give you an give us an example. So when we talk about the terminating decimal, it's let's say example here. For example, when you have 0.5, 0.5 is terminating decimal because after the decimal point, you see you have only one number. Okay, something like 1.25, even 3 is also a terminating decimal because you see that here we have 1.2553. So after the decimal point, you can count the number of digits, 1, 2, 3, only 3 digits. Now, all of this type of numbers, they are easily rational numbers because you can write them in form of A over B. For example, this one is just 5 over 10. And this one, you can just write it as what? 1, 2, 5, 3 divided by 1, 2, 3. So let's say 1, 2, 3. Right. So these ones are easy to see. Then there is another class which we call the non-repeating. For example, repeating decimals. For example, if you have, let's say, 0.333333. So you see, this is continuing. This is like there's a pattern for it. So it continues. Another example is something like we can write this as 1.21 bar. So all of these are examples of rational numbers, because what this means is simply 1.2111, and we can actually show that these numbers can be written in the form of A over B. But we're not going to do that in this short video. Now, let's go to another class. So from this rational number, so let's move to this one. Put it this way. Here we can have, this is still bigger. So this is the real number. So now what is left is the other part, classification. There are other number which we call them irrational number. So let me put them here. So this is what we call the irrational numbers. And you can denote them by maybe H. Some texts use I. Now, what is irrational number? Irrational, they are just the what? They are just the opposite of what? Of rational numbers. In other words, they can be classified into two, which we call non-terminating and non-repeating. Okay. Now, when we say non-terminating and non-repeating, what does that mean? It means, for example, let me just give us an example. You have something like, let's say the typical example is pi, right? And we know that pi is not 22 over 7. So pi is about 3.1425. You know, the numbers will continue. It doesn't repeat. And the digits, it doesn't terminate. So we can also have another example like 0.10, 100. Okay, let's say we have 10001001110. So if you look at this number, these digits, there is no specific pattern for it, unlike this one where you have 333 and here you have 111 will continue. So this is what the type of numbers we call non-repeating. Another example is any number in the form of this, for example, square root of 2, square root of 7, cube roots of, let's say, 11. All of these numbers, they fall under category of irrational number. So here, just to conclude this part, we will see something here that you see that every natural number, we can say that is why we have this arrow going up, right? So it's true that every natural number is a what? Is a whole number. And every whole number is what? Is an integer. And every integer is a rational number. And you can see every rational number is a what? Is a real number. So, and here also we can see from this part, the right-hand side, you see that every irrational number is also what? A real number. So, in summary, we can say a real number is categorized into two different parts. There is either a rational number or an irrational number. And so this is the classification or the types of numbers we have in this chapter P. Yeah, so this is P2. Now let's go to something else and talk about the properties of real numbers. So let's talk about properties now. So here, this is still part of P2. So we're talking about properties of real numbers. Okay. Now, when you talk of properties of real numbers, about three things are important. So here, let me write this. Let me talk about the properties. And here, I will put what we call the addition. On here, I'll put multiplication. So we are talking about this property based on two operations, based on addition and what? And multiplication. So the first property we'll talk about is, we'll talk about closure. Now, what is closure? Closure simply means if you take two numbers, let's say A, B, these are two real numbers, then you are sure that what? A plus B is also in what? In R. So this is true for real numbers. If you take two real numbers, A and B, if you add, the sum will still be in R. For example, if you take 2 and 3, you see that 2 plus 3 is still in R. So this is what I mean by closure. And similarly, it also holds for the case of multiplication. If we take A and B in R, and we take what? A plus R, A times R, sorry, A times B, this is multiplication, is also in R. So if you take 2 and 3 in R, 2 times 3, which is going to be 6, is also a real number. So this is what we mean by closure. Then the second one is what we call commutative property. So commutative property, so here we talk about property, here we talk about the operation. So commutative under addition, it means if you take two real numbers, A plus B is the same thing as what? B plus what? Plus A. For example, if you take 2 and 3 again in R, you see 2 plus 3 is the same thing as what? It's the same thing as 3 plus 2. Also, under multiplication, if you take A, B in R, you see A times B is the same thing as B times what? A. Let's take different numbers. Let's say, for example, you take -1 and you take 3. You see, these are numbers in R. Both of them are real numbers. What is -1 times 3 is the same thing as what? 3 times -1. So this is what we mean by commutative. So the property is important. So we say commutative under addition. So we're talking about this one. Commutative under multiplication. We're talking about this one. Now, let's talk of the third property, which is associative. So for associativity, we need to think of three numbers. Let's say A, B, C in R. Then here you can have A plus B plus C is the same thing as what? A plus B plus what? Plus C. So this is saying that the order is not important. You can decide to start, you want to add three numbers, you can decide to add these two first, the last two. Then before you add the first, or you can add the first two before you add this one. And in terms of multiplication, the same. If you have A times B times C, you can have it this way. It's the same thing as AB multiplied by what? By C. So the order is not really important when you have three. So there's an associate. You can associate these operations. So now here, number 4. Here there's no particular example, but it's easy to see. For example, if you take 2 plus what? 3 plus maybe 5, we're taking all positive here, is the same thing as 2 plus 3, all plus what? Plus 5. The same thing. If you take 2, you multiply 3 first. 3 times 5. This is nothing but what? It's still the same thing as 2 times 3 times 5. So here, what do you get? You'll get 2, and this is what? This is 8 plus 2. This will give you 10. And this is 5 plus 5. This is 10 as well. This, you start with this to give you 15 times 2, which will be 30. And you start with this 6 times 5, which is still 30. Then number 4 is what we call the let's call it identity, right? So if you call it identity, what is identity? It simply means if you take any A in what's in a real number, so this means real number. So you see that what? A plus 0 is still going to be what? It's still going to be A. So this is what? It means we have the identity. It means in real number there is an identity in terms of addition, and that identity is what? Is 0. Because if you take any real number, you add 0 to it, you still retain the real number itself. Why in the case of multiplication, if you take any A in R, you see that A times 1 is still going to be what? It's still going to be A. So in this case, 1 is the what? Is what we call the multiplicative identity. Why here 0 is what we call the additive, we can say identity as well. Okay, so this then number 5, we have what we call the inverse. So what is inverse? Inverse means if you have, for example, you take A to be in what? In R. You see that what? If you have A plus what? Minus A, you're going to get what? 0. So this minus A is what we call the what? We can call it the additive inverse. For example, if you take 2, you see 2 plus minus 2 is going to give us 0, which is, remember, is the identity. So we can say that minus 2 is what? Is the additive inverse of 2. If you take maybe 3, let's say we take minus 3, you see minus 3 plus 3 is going to give us what? 0. So it means that 3 is the additive inverse of minus 3. Okay, now in this here also, in terms of inverse here, what do we know? If you take any A in R, we take the reciprocal. You see that A multiplied by 1 over A is going to give us what? It's going to give us 1. But here we know that A should not be what? A should not be 0. So what does that mean? It means that what? 1 over A is what? Is what we call the multiplicative inverse. So now, but here we can see that A, if A is equals to 0, then we have a problem, right? So every number has a what? It has a multiplicative inverse, except what? Except 0. All right, there are some certain set of real number which we call the interval. And these intervals are very important because they form part of the real numbers. So for example, if you have a number line, is your number line, and this number line has every number that we're talking about that we need. We have both for example, this is 0, and here we can have 1, here we can have 2, 3, 4 continuously. This is minus 1, minus 2, minus 3, right? Minus 4. So all of these are real numbers. And you can see we can have, for example, between minus 1 and minus 2, we can have minus root 3, which is also a real number. And between, let's say, 0 and 1, we can have something like 0.1, right? And let's say between 3 and 5, we can have something here which is called pi, right? Because pi is about 3 point something, yeah, so which is here. So this is a number line. You have all the type of numbers that we're talking about. We will have irrational, we will have rational, we will have integers. For example, this is an irrational number. And we can see that 0.1 is nothing but a rational number. Yes. And we can see that minus 3 is what? Is an integer. Right? So different types of number that we can locate on the number line. But talking about interval is used to what? It's used to describe a specific set of real numbers. And for example, I'll just give us what are the types of interval that we have. For example, we have close interval, which we call it, let's say, AB. And so what does this mean? In terms of inequality, this is referring to every real number, such that what? That real number is between A and what? And B. So this is in terms of interval. And now we have written it in terms of what? In terms of the inequality. And what this simply means is that we can write this. So let me have something like this here. Here, let's call it interval. And here we can say we call it inequality. And here we can have a graphical representation, right? So what does this mean? This means on a number line, you're to pick every number between A and let's say this is A and this is B. So every number between A and B included, is what this interval is talking about. Simple example, if you take, let's say you take this to be 2 and 3, this means you need all the real number between 2 and what? And 3. So this means that you can change here to what? To 2 and change here to what? To 3. So this is what interval is talking about. And this is important because in real line is ordered. What do I mean is ordered? This means you can compare numbers, right? And that means we can compare between A and B. If you take two numbers here, for example, 1 and 2, we can say that 1 is less than what? Less than equals to 2, right? Or we can say 2 is bigger than 1. Then this is one type. Then another type of interval is what we call the open interval. So this is what we call closed. And this is what we call the open interval. So for the open interval, you're taking all the real numbers between A and B. But in this case, both A and B are open. So we have something like this. If this is your A, this is your B. So both of them are open. And down you have this. Then you have what you call half closed, half open, and all of that. So we have, for example, if you have A to where, and let's say A is closed and B is open. So it means that you will have the equality around A and the B will be open. So here it means that A, it will be closed, but at B, it will be what? It will be open, right? So it's open here, but it's closed here. So you have all the real numbers here. And if you take it the other way, so this will be, it means you can open it here and you can close it here. So these are various types of interval. And when we have infinity, for example, if you have minus infinity to infinity, this is telling you the whole of real number, right? Just the real line. Now, let's see just one example here. And let's say, for example, we say express maybe say minus 1 and 2 in terms of inequality. So what does this mean? This simply means that you write these as what? Just minus 1 and what? And 2. Since it is closed here, you can close it here, and here you what? We open it. So that's it. We're done. All right. So now let's talk of sets. What is a set? If we talk about sets, we said set is just a what? It's just a collection of objects of some type. Yes. So we say that, and each member of it is known as what? Is known as an element. So for example, we can have a set we can call set A. It's just, we can say this is A, B, C, D. So this is just a set of what? Consisting of what? Of 3 or 4 letters. So each of these letters now, A, B, C, and D, they are member of the capital of this big set, which is set A. So usually we denote a set by capital letter and the elements by small letter. So let's see another set which has to do with numbers. So we can do set B, and we can say it's just a set consisting of numbers 1, 2, 3, let's say 4 up to 10. So this is also a set of numbers. And if you look at this, you see that when we have a set, something is usually common. If you look at this one, these are set of alphabets, right? And why these ones are what? Set of numbers. So there is a kind of something common for all the elements. So they are of the same, of similar type. So for example, we can have another this, and we say this is a set C consisting of what? Of, let's say, mango, orange, and we can say strawberry. You see, now this is a set C. So set C is just what? Is consisting, is a set where you have the elements of the sets are just fruits, right? And so you see there is some, that is why we, in the definition, we said an object of some type. It's very important. But let's go to define some things about sets, which might be of interest. So let's talk about the first one, which is called the equality of sets. So if you have two sets, A and B, they are equal if and only if. When do we say two sets are equal? If and only if A and B have exactly the same what? The same element. So if this happens, then we can say, for example, if you take set A to be 1, 2, 3, 4, and 5, and set B, we can say set B is just X, such that what? X is a what? Is a natural number. And let's say X is less than equals to 5. So if you look at these two sets, they are exactly the same. There is nothing different. It's just how, it's just maybe how the sets are being defined. So this is 1 to 5. And here you say B is X. X is a natural number, right? We know natural numbers start from 1, 2, 3, 4, 5. Yeah, and it's less than equals to 5. So you can see that exactly that A is the same thing as what? Is the same thing as B, because they have exactly the same number of elements. So we say not just the same number of elements, but the same element. So we say this is equal sets. But if you have another set, let's say D equals to, you have 1, 2, 3, 5, 6, and you have, say, 4. Remember, in set, the order is not important, which one comes first or not. And here we can see that A is not equals to what? It's not equals to D, because we have an element here which is not in what? In A. All right. So let's talk about another thing here. We talk about subsets. So when we say subset, we say A is a what? We denote subset by this. This is meant by subset. If what? And only if. We can say just if what? Every element of A is an element of what? Of B. So an easy example is this one. Let's say we took A Remember we said our A is what? 1, 2, 3, 4, 5. Let's maintain the same A. And now we maintain the same D. But now let's write D. Okay, let's maintain the same D. Let's say we say D is 1, 2, 5, 6, and 4. Now look at A and D. We can see that every element you take here, take every element here. Is it an element here? No, because here we have 3, but here we do not have what? We do not have 3. So let's modify this one, and let's say to the D, we add 3 to it. So you see now that every element you take from A is an element of what? Of D. For example, you take A, you take 1, 1 is also here. We take 2, you see that 2 is also here. We take 3, we see that 3 is also here, 3 is here. We take 4, 4 is here. We take 5, 5 is here. So we can say that A is a subset of what? Of D. Because every element of A is an element of D. But can we say that D is a subset of A? No, this is not true, but this is true. Why this is not true is that what? You, for example, take 6 from D. So you see that 6 is an element. So for element, we use this symbol, is an element of D. But you can see that 6 is not an element of A. So because of this, this is not a subset. But in this case, it's good because every element of A is an element of D. So that is that about the quick one about subsets, just to remind us. Okay. Then now let's talk about a finite, a universal set. Let's talk about a universal set. So when we talk about a universal set is just, we said is the, it's just a set that contains all elements, we said, in the universe of discourse. Now, what do we mean by this? It simply means that what? Let me just this with an example. Let's take a U to be equals to 1, 2, up to 10. And we take an A just the same as 1, 2, 3, 4, 5, right? Let's stop here. And we take a B to be just 2, 3, 4, and 6. And we take a D to be 1, 2, 3, 4, 5, 6. Now, if you look at this set, you know, both look at A, B, and D. They got all their elements from where? From U, right? So it means that U is like what? Is the mother set. I mean, it's all the elements, all the other set derive their elements from set U. So it means that what? U is the what? Is the universal set because every other set got their elements from set U. So that's what we mean by a universal set. Another example of a universal set is R, which is the whole real number. So we can say U is equals to what? R. And what is R? Minus infinity to infinity. Because if you look at this, every other set that we've talked about, like natural numbers, like the integers, natural number, rational numbers, like the integers, you know, they all part of where? The real numbers. So the real number is like the the mother set, because they derive their element from there. Okay, so that is a quick one about universal set. Then let's talk about finite and what infinite set. So what is a finite set? Finite set, simply what is any set that has what finite numbers of elements. So what do you mean by finite numbers? It means you know the number of elements, you can count them. For example, if you look at the A we talked about, let's say 1, 2, 3, 4, 5. Yeah, this is finite because you know how many number of elements we have here. We only have 5 elements. These have 5 elements only. And let's say we have let's say you have another set which you can define as B. Let's say you have 2, 4, 6, 8, 10. This is also finite because it has 1, 2, 3, 4, 5. Let's even make it 12, right? So this has 6 elements. Now, let's see something. For example, the natural number, it is 1, 2, 3, these ones, you cannot what? You cannot count the number, right? So this is talking about infinite now set. So we cannot count the number. For example, even the integers, they have both positive and negative. So this type of numbers, this type of set that you cannot count how many number of elements they have, they are called infinite set. So for example, now if I give you an open interval 0, 1, close, this also is telling you that this is also an example of infinite set. Because of what? This is telling you that all the real numbers between what? Between 0 and 1. And we cannot exhaust them, we cannot count them, right? We cannot count all the real numbers between 0 and 1. So this becomes an infinite set. But take notes, try to get a difference between this one and this one. If you have a set with a braces and this one is what is finite. Because this is just telling us that is a set of numbers, just 0 and 1. Why this one is telling us it is all the real numbers between 0 and 1. So this is infinite, while this is finite. All right. So now let's look at the operation of sets. Or we say what are the operations on sets? For example, we have this question. We let U, this is the universal set. You have A is this one, B is this, and D is this. So we want to just use this example just to look at some operations that we can perform on set. One of those operations is this, which is union. So we have A union B. So how do we find union? To find union, you just need to take every element that are in A and element that are in B. So this is our A and this is our B. So you can see we have 1, so we can take 1. And here you see we have 2. Here we have 2, but you don't have to repeat it. So just take only 1, which is 2. And okay, here we have 4. We also have 4 in A and B, but you take it once is okay. Then we can take 5. Then we have 6 here. And we have 8 here. And then we have 10. So I think this is A union B. So you take elements that are both A and elements that are also in what? In B. But don't repeat. So there's no need for repetition in a set. So once you have, like here, you have 2 here, and you also have 2 here. Taking it once is enough. Okay, then that's number 1. So number 2, it's D prime intersection C. So first of all, let's find what is D prime. And D prime, this means what? Complement. So complement simply means take all the elements that are in that what? That are in the universal set that are not in the element. So for example, this is D. This is D. If you want to get D complement, take every element that are inside what? So D complement, by definition, is all elements that are in the what? That are in the universal set, but are not inside what? D. So that is the definition of D complement. So it means that D complement, let me write it again, is every element that are inside U, but what? That are inside U, such that what? That element is not inside what? D. So if you look at our set now, where is D? This is 2. So you can see there is 1. 1 is in the universal set, but it's not in D. So it means we'll take 1. We also have 3, which is in the universal set, but not in D. You see we have 4, but 4 is also in D, so we cannot take it. We have 5, so we can take 5 because 5 is not in D. And 6 as well. So we can take 6 because 6 is in universal set, but it's not. Okay, we cannot take 6 because 6 is already in D, so we can take 6. What else? We took 5, yes. What about, okay, 7 is already here. 8 is also here. 9 is also here. So what is left, I think, is 10. So these are the elements that are inside the universal set, but are not in what? In D itself. So this is D prime. So now we need D prime intersection what? Intersection C. So what this simply means is, what is our D prime? Our D prime is 1, 3, 5, and what? 10. And we intersect it with our C. What is C? Do we have C? D intersection C. I think we don't have C, so I think I mean B here. It should be B here. Okay, so what is B? B is 1, 2, 5, and what? And 4. Is that okay? So now let's look at the intersection. What is common between these two sets? Intersection simply means what? What is inside D prime and what is inside B as well. So you see here there is 1, there is 1. So it means in the intersection we'll have 1. There is 3, there is no 3. So there is 5 and there is 5. So I think this is just the intersection. So this is just a quick review on how to perform operations. Intersection means take what is common to both sets. And so let me just, if you have two sets, you said A intersection B, what does it mean? It's simply you take elements that are in A and what? Elements that are in what? In B. If you need A union B, you take elements that are in both A or elements that are in what? In B. Then if you need the A prime, which is the complement, you take elements that are inside the universal set, but not in the set itself. All right. So we look at now I think the last part of chapter P2. which is the absolute value and distance. So if you have any real number, so let's have the definition here. It says if A is a real number, then the absolute value of A is what is simply given by this one, is equals to A if A is positive or 0, or it is minus A if A is less than what? Than 0. So this is simply what we mean by the definition of an absolute value. And it can be seen as the what? As the distance between any real number and what? And 0. So for example, the distance between here, between A minus A and 0 is the same thing as distance between A and what? And 0. So this distance is simply what is given by absolute value, because the distance cannot be negative, right? We know distance cannot be negative. So we can see an absolute value as the distance between A, the distance between this A and this what? 0 is going to be A, right? Yeah. And also the distance between minus A and 0 is still going to be A. So, which is this? Because here we're saying that an absolute value of A is just A. If your A is positive or what's equals to 0, and then it is minus A if A is less than what? Is less than 0. For example, in this case, if you take minus here, it's less than 0. So it's going to be minus minus A, which will turn out to be just a positive. The distance is always positive. So for example, let's see. If you have absolute value of minus 3, it's just going to be what? It's just going to be the same thing as 3. Why? Because this is negative. So based on the definition, you see the quantity is negative, then you'll have the final result is just going to be minus minus 3, which is going to be 3. Because it's going to be minus A, but A is minus 3. So you have minus minus 3, which is 3. Then also if you have something like 3 minus pi. Now if you look at 3 minus pi, you can see that what is the quantity inside? 3 minus pi, you see, is a negative number. Because of what? Because 3 is less than pi. Now, since what is inside the absolute value is negative, it means your A is less than 0, right? So it means you're going to have minus A. So to remove the absolute value, it means you're going to have minus A. But what is our A in this case? Our A is 3 minus pi. So it means it's going to be minus 3 plus pi, which we can write as pi minus what? Minus 3. And why do we have this minus? It's simply because, you see, because we have 3 minus pi is less than 0, yes? It means it's negative. So it's less than 0, it means we are in this condition. So we'll have minus A. All right. So let's have another one. Let's say, for example, we have, just say, absolute value of x minus 1. And we have a condition that our x is between 0 and 1. So this one also, if x is between 0 and 1, it means that what? This number here, just take any number between 0 and 1. 0 and 1 is just like open interval 0 and 1. If you take any number here, let's say half, right? If you take 1 over 2, you put it here, 1 over 2 minus 1 is going to be also be a what? It's going to be a negative number, right? So all you need to do, it means this one is to become negative here and minus x. So this will be minus x plus 1 will be the answer. So for us to deal with absolute value, you just need to know the quantity. What is the quantity under the root? So let's talk about when we're looking for the distance between two real numbers, say A and B. This we say it's just what? It's just the absolute value of A minus what? Minus B. So if you have two real numbers, say this is could be 0, this could be A, this could be B. So if you want to find the distance between A and B, it's just the absolute value of A minus B. And this is also the same as absolute value of B minus A. All right, now let's just take, to conclude this video, we'll take some few questions here. Now, which of the following statement is true? Every rational number has a multiplicative inverse. This is not true because here, talking of multiplicative inverse, for example, if you take A equals to what? 0, the multiplicative inverse will be the reciprocal. And if you take, remember, when we talk about multiplicative inverse, it means you should have A times 1 over A to give you what? To give you 1, which is the identity. But under multiplication, but if you take A to be 0, you see the reciprocal 1 over A is going to be 1 over 0. So this is undefined. So it means A, and we know that 0 is a rational number. So 0 is a rational number, but it doesn't have a multiplicative inverse. So this is not true. Now, B is true because every irrational number, B is false, yes, because irrational number is also a real number. But here it says it's not a real number. But look at the question. The question is looking for the statement that is what? That is true, right? So since it's looking for the statement that is true, we need to look for the true statement. Here, every rational number has a multiplicative inverse. So let's put it here. This is false, right? Okay. Here, every irrational number is not a real number. This is also false. Okay. Now, every even integer has an additive inverse. This is what is true. What do you mean by an additive inverse? If you remember, we said an additive inverse means A plus what? Minus A to give us what? 0. So it means that what? Minus A is the additive inverse of A. So take any even integer, just take the negative of it. Then you add, it will give us what? 0. For example, if you take 2, which is an even integer, you add plus minus 2, it will give us what? It will give us 0, right? Yeah. Okay, so this is true. Then pi is 22 over 7. This is false because pi is not even a rational number. If you say it's 22 over 7, then you're saying it's a rational number. But we know that the value of pi is about 1.44, I think, 4.5 something, you know. It's an irrational number, so you cannot write it as 22 over 7. Then the sum of two rational number is always what? Irrational. This is also false. Simply because, for example, if you take root 5, the sum of two rational number is always what? It's always irrational. Okay? This is not true. Why? Because let's take some rational numbers. If you take rational number, for example, 2 plus 5, both are rational numbers. If you add, what do you get? You get 7. 7 is still a what? Is still a rational number. So this is not a true statement, because this one says the sum of two rational number is always irrational. This is false. Okay, let's see. Look at this one. This one says, which of the following sets are finite or infinite? So we just need to determine. So here, let's just have an idea. So when we say sets of months of a year, what are the set of months? We have from January, and we have February up to December. So these are the months, and you can see it is what? It is finite. So because you can count them, so this is finite. This one, you have number 1, 2, 3. This is just like the set of natural numbers. You cannot exhaust them, you cannot count them, so they are infinite. And here you see that this one's is finite because you have 1, 2, 3 up to 100. And here the set of positive integers greater than what? Than 100. So this one you cannot exhaust it, because positive integers greater than 100, you can start from 101, 102, and you keep going. So this is what? This is infinite. Then the set of prime numbers less than what? Less than 99. So definitely this is going to be finite, because you can count them, starting from 2 up to starting from 2, it's prime, 3, 5, 7, and you will stop at where? Less than 99. So we will have something 99. So what is the prime number? Less than 99. Maybe it could be maybe 90, maybe 97. Okay, so these are only prime numbers, and you can see that it's going to be what? It's going to be a finite set as well. So this is a finite as well. So the only infinite set here, this is infinite, and this is also infinite. Now, look at this question. This question says that what? The number of irrational number in the set, this. So you're looking for the irrational numbers. So what will be the irrational numbers? You have to look carefully here. You're interested in the irrational number. Now on this one, the first one here, you can write it as minus what? You can put the roots together, so it becomes this. And now this will become 1 by what? By 4, which is simply over what? So this is just going to be this one. So you see, it is no longer what? It is no longer an irrational number. It becomes a rational number, because you can write it in the form of a over b, where a and b are what? Are integers. So, but it's in this form, you have to what? You have to rewrite it so that you can put this the roots together, since they have the same index. So it means that this is not a what? It's not an irrational number. Now, if you go to the second one, the second one definitely is not, because this is what? This is minus 3. So this is not irrational. Remember, we're looking for irrational. Then here we have square root of what? The minus square root of 27. So we know that 27 is not a perfect square. So surely this will be the first one. So this is irrational. So let's tick. 0 is a rational number. So this goes. And here, what do we have? We have 1 over root 9. 1 over root 9 is the same thing as 1 over 3, which is rational. So this is also not included. Then the next one is, which one? 1, it's what? It's an integer, so it's a rational number. And here this is also irrational because you have pi. Pi, we know it's irrational. Multiplied by 2 is still irrational, right? Then what next? The next one is this is what? This is rational, so it is not irrational. Root of 12. Root of 12. 12 is not a perfect square, so in this case, this is going to be another what? Irrational number. Okay. Now, if you look at this one, this is 3.14. 3.14 is not, you can see, this belongs to what we call the terminating decimal. So you can easily write it as 314 over what? Over 100, what becomes rational. So it means you cannot take this one. Then the next one is this one. You can see this fall under the category of what we call non-repeating, right? It's non-repeating and non-terminating. So you can see there is no specific pattern. This is 1,5, this is 1,15, this is 1,115. So this makes it what? Irrational. So we have how many irrational numbers? We have 1, 2, 3, 4. And so this is the answer. All right, let's discuss this one else. So which of the following statement is false? Every rational number is either what? Even or odd. Every rational number is either even or odd. So we are looking for the statement that is what? That is false. So what are even numbers? Even numbers are any numbers you can write as a multiple of 2, right? And so any number you can write as maybe 2 times k, where k is an integer, we say that number is what? That number is even. And any number you can write as, let's say, 2 times k plus a 1, where k is also an integer, we say that number is odd. Okay, now let's do by elimination. So every rational number is either even or odd. Okay, now let's move. We'll come back to that. Every real number is either rational or what? Irrational. So this is what? This is a true statement. Remember, we did the classification of real numbers. We said real numbers is divided into rational and what's irrational, right? And we have classification under rational. You have the integers, you have the whole numbers, you have the we have the natural numbers and all of that. Okay, so this is a true statement. Now this one, C, all repeating decimals are what? Are natural what? Numbers. So repeating the rational numbers, repeating decimals means what? It means repeating. For example, we saw something like this. It means there is a pattern, right? For example, 5.3 bar. All these are rational numbers. Now this one, 8 bracket x plus y plus 5 is equals to 8 yx plus 5 represent what? The commutative property of multiplication. Now, is this true? Multiplicative, what? Is talking about commutative property of what? Of multiplication. Now, this is also true, right? Now, why is this true? This is simply true because if you look at what is changing here, it's just what? Xy becomes what? Yx. And when we did commutativity under multiplication, we said AB is the same thing as what? Is the same thing as BA. So it means if you multiply A times B, it's the same thing as B times A. So this is what we mean by commutative under multiplication. While under addition, we said A plus B is equals to what? B plus A. Is that okay? So this is also a true statement. Okay. Now, the multiplicative inverse of 5 1 over 4 is this. Now, all you need to do is take this number, which we can write as well. This is 4 times 5. This is given in terms of mixed fraction, so we can write it 4 times 5 plus 1. So this is 21 over what? Over 4. So this is our A. Now, this is our A. A is equals to this one. And if you're looking for the multiplicative inverse, it will just be the reciprocal, which is 1 over A, which is just 4 over what? 21. Yes. And you can see, if you do A times 1 over A, it's going to be 21 over 4 times what? 4 over 21. This will cancel this, this will cancel this. You have 1, which is the identity under multiplication. So this is also a true statement. Now, so let's go back to the option A to see why it is false. Remember, I earlier said that for even numbers, you have to be able to express even number in this way as 2 multiplied by k, where k is an integer. And for odd, you have to be able to write it as 2k plus 1, where k is an integer. But for example, if you take a rational number, say 1 over 2, now if you look at 1 over 2, 1 over 2 definitely, it's a rational number, right? But can we write it as either even or odd? No, because for us to be able to write this as even or odd, we should be able to write it as 2, for example, even. We should be able to write it at 2 times a number where that number k must be what? Must be an integer. But here we cannot do that. So you see that what? This cannot be an even number because there is no way you can express half as 2 times an integer. And you see, and for you to get a half. So this is not possible. So for example, if you try to use 1, you'll have 2 times 1, but 2 times 1 is even bigger than half. So what this means is this. This is a rational number. You cannot write it as an even. It's not an even number, and also it's not what? An odd number. So it means that this is what? Is false. Okay. So let's move to another question. Here is a question about absolute value. we have the condition that x is less than what? X is less than 0. So if x is less than 0, it means you can take any number between minus infinity to 0 open, right? And for us to remove the absolute value, we need to check what is the quantity inside the absolute value, right? So for example, we can take x, let's say you can just test x to be maybe minus 1. If you put minus 1 here, inside this first absolute value, you'll have minus 1 minus 2 over 3. So it's a negative number for sure, right? But here, if you put minus 1 here, you're going to have 1 over 6 minus minus 1, which will be 1 over 6 plus 1, which becomes a positive number. So we're not interested in the value, but we're just interested in, not in the quantity, but in the sign. So since this is negative, then to remove the absolute value, another negative has to come. So we have this, right? Then minus here, since it's positive, we can just remove the absolute value and write 1 over 6 minus x. So this minus is coming from the question, this one here. This is positive, so we can just remove the absolute value and we have this. Now if you expand this, we have minus x plus what? 2 over 3. Then here will be minus 1 over 6. Minus minus will give us what? Plus x. This minus x will cancel this one. And so we have 2 over 3 minus 1 over 6. And here, what can we do? We can try to make the LCD to be the same by multiplying by what? 2 over 2. So this is just 4 over 6 minus 1 over 6. And this is 3 over 6, which is 1 over 2. So we're here. Then similar question here. This expression simplifies to, now same thing. Here this is root 5 and this is pi. We know pi is 3.14 something, right? So which is greater than root 5. So this is going to be negative. Surely, because we know root 5 is what? Root 5 is less than 3. Yes. So here, this is 2. And now you need to know what is 2. What is the, when you compare 2 and root 5, which one is what? Is bigger and which one is bigger? But what do we know? We know that what? We know that 4 is less than what? Is less than 5. And 5 is less than 9, right? So this is what we know. And we know that what? So we have root 5 is going to be less than what? And this is this one. This is true. Because we know the root function. So this is increasing, right? Okay, so if you look at this, you see that root 5 is going to be what? Is going to be greater than what? Then because root 4 is what? Is 2. So 2 is less than what? Root 5. And root 5 is less than 3. So what does that mean? It means that when you say 2 minus root 5, this is actually greater. So this is going to be also negative. Is that okay? Now that we know that both negative, and we can also use the same argument here. Remember, this is root 3, and this 3 is actually less than pi. So we can say from here, you see that between root 5 and pi, which one is bigger? So you can see that root 5 is actually less than what? Than pi. And that is why we said here is also negative. Okay, now let's come back here quickly. Now we know both are negative, so we can put minus here. So this is root 5 minus pi. Here is also, this plus is here, but this is also negative, so we have another negative coming down. So we have 2 minus root 5. So this will become minus root 5 plus pi. Then this will be minus 2 plus what? Root 5. And here what will happen is that this and this will cancel. So you just have this pi minus 2. And this is the answer. Okay, so this is the end of the video. This is the part 1 of the review of chapter P. So this is basically just P2. So watch out for the next video, which will contain P2, P3, and P4, the quick review. Thank you for watching, and don't forget to share with your friends. Let's go back to the first one, and let's say why this is not true. If you look at